My name is Viktor, and I work at Algoryx Simulation as a senior scientist. And in this talk, I want to argue that, at least from my perspective, I think that physics is actually one of the main bottlenecks right now that is preventing us from reaching this next generation of vehicle autonomy. So I really think that if we want to have AI-controlled excavators, and that's what this talk is about, and we want to have them that they behave robustly in the real world, they need to be able to handle contacts, terrain, and machine dynamics in a way that it's actually part integrated into the intelligence system. So what we do at Algoryx is that we focus on autonomy for heavy vehicles, and in particular, how they interact with the terrain. And this makes us a very good fit in XSCAVE, which is a EU Horizon project, and it has the overall aim to advance terrain adaptive autonomy for excavation and forestry. And I'm going to focus on the excavation part. Now, our contribution to this project, it's on the simulation and autonomy side. So what we do is that we build the digital twins, and then we connect them to the learning-based control. And as you see from this to the left here, the consortium is very strong, and it's spread out across academia and industry. And although we're not even, I think we're like 1.5 years into this project, there's already some quite interesting development going on, and I'm going to talk about that next. So one such initiative is called XSCAVE, and the very basic way to describe this is to say that it's like Isaac Lab, but it's targeted for heavy vehicle terrain interaction. So the short version is that it's a framework for building scenarios and learning and evaluating autonomy in conditions that are difficult, expensive, or unsafe to explore directly on the real machines. Excavation being a prime example of this. And next, I'm going to show you an example of how a simulation framework like this, XSCAVE, can fit into a larger autonomy stack. So in this work, and the video is running, yeah, we're exploring how to build an interactive excavation on top of that simulation framework. So the way that this works is that this agent, it takes human input, and then it reasons about this task, and then it uses its specialized tools or skills, whatever you want to call them, to try to solve this task. And it can be anywhere from kind of low-level to high-level tasks. And yeah, just to set the expectations here, we're definitely not excavation experts at Algoryx. So the point here is not to have some kind of perfect task execution, but just to show physically grounded autonomous behavior. And in this video that we're looking at right now, it shows an example of me prompting this agent. So in the beginning, I just gave it a bunch of random tasks, and then I asked it to finish the trench that was straight in front of it. Then in the end, I just interrupted it and asked it to drive to the center of the map and raise the bucket to as high as it could. So I've listed some of like the tools or skills that this has to the right. And among these, by far the most challenging one is the digging policy. And the reason for that is because that's actually where the bucket interacts with the terrain. So this is a reinforcement learning policy, and it's already quite capable at digging. It can dig in quite a variety of different scenarios and different terrains. But of course, if we move this reinforcement learning policy, as is always the case with RL, outside of the training domain, then it will naturally fail. So an example of such a harder case where the policy we just saw would definitely fail is this. So here we have a terrain that contains an embedded rock. And here the operator's task is to extract this rock. And now this is not reinforcement learning, it's a person controlling this thing with a gamepad. So now in this case, we have soil tool, we have a rock tool, and we have rock terrain interaction all at once. And this makes this kind of behavior really, really hard to model and predict, because if we have small changes in some kind of contact conditions or terrain conditions, then it can result in very different kinds of motions. And I think this is one of the reasons why tasks like these are challenging, very challenging for if we want to use conventional control, but even sometimes for experienced operators, if I understand it correctly. So my point with this is that I think that if we want to have autonomous excavation to be both robust and efficient, then we need simulations that capture these kinds of effects well enough for training, testing, but maybe most importantly, failure analysis as well. Then we also have this, that if we want this simulation to actually be useful, then it somehow needs to be validated against reality. So this video, it shows a comparison between motions from the simulated and the real vehicle when we send a step response to the boom joint. So the way that this works is that we have recorded data from the real world, and if you follow this left branch giving the simulation, then we take this real world data, we extract the joint commands, we send them to the simulation, and that results in some motions. And that's what you see to the left. We can do a similar thing for the real motions. From the same data, we just extract the joint transforms, and then we visualize them as you see in this very simple animation that I created here, which says real. The important thing with this is that this gives us a practical real-to-sim workflow. So we can record on the machine, we can replay offline, and then we can compare responses and tune the simulation model until we think it aligns well enough with reality. So if we don't have this kind of loop, then the simulation is just an animation. But if we have this loop, then it becomes an engineering tool for building autonomy. Yes, so I just want to finish this off by saying that for autonomous excavation, I think that good models, good contact physics, and good real-to-sim validation are not something that should be considered optional. I think they are one of the most important things if we want to have high-performance autonomy. So thanks for listening.